Hey everybody, welcome to this week's lesson for physical science. Okay, we're going to be talking about wave stuff. I got really technical this week, all right, with my title, but a little bit more technical. Specifically, we're going to address the topic of speed. How do you find the speed of a wave? And then also light. Okay, what is light? I know we've talked about light as energy and as a wave, but light's a little bit more mysterious than that. So we'll kind of look into that, and that's kind of an interesting thing that I like to teach. So yeah, let's jump in here with both feet. Some review stuff, you guys. Okay, we got waves. There's the definition. By the way, remember, if it's underlined, you kind of want to write it down in your notes, right? Okay, that's really helpful. So there's a wave definition, right? And waves have two important parts, okay? You have wavelength. That's the distance between two similar points on a wave, and that can be any two similar points, right? And then we also have frequency, which is the number of wavelengths that pass in 1 second. Okay? And so a little bit more about wavelength and frequency. And again, this might be review for you. So wavelength has this symbol right here. This is called a lambda. It's actually a Greek letter. You can say that with me, lambda. Yeah. So any two similar points, and we measure it in meters, you guys. Okay? Then the other one is frequency, which has a, this is actually a Greek letter too, but it looks like an F, so that makes total sense. The units for frequency, remember this, are hertz. So hertz means per second, okay? Wavelengths per second. All right, now in general, there's a relationship between these two things. The higher the frequency is, the shorter the wavelength, and the lower the frequency, the longer the wavelength. Okay, because hey, when we've got shorter wavelengths, we can pack more wavelengths into 1 second, right? Okay, cool. So moving along here. All right, we're going to look at this equation today, and this is how we'll spend the first half of our little time together here. We've got the wave speed equation, right? The velocity of a wave, right, is the V, is equal to wavelength is equal to frequency, and then wavelength, right? Remember this funky thing here is wavelength. So wave velocity, the speed, is equal to frequency times wavelength. All right, awesome. So how do we kind of apply this? Well, the big thing with formulas is this, you guys, can you rearrange it? Okay, can you make it so that you can find whatever you need? So it's easy to find velocity, right? Velocity equals frequency times wavelength. So that's easy. What about if we want to find frequency? Well, here's our original equation. And we're going to use just some quick algebra skills, see if we can rearrange this, you guys. So if I want to find frequency, that's this F right here, right? So how do I get that by itself? Well, I'm going to divide, because the opposite of multiply is divide, right? If we're multiplying here, we're going to divide to kind of undo it. So we get those guys set up, right? And if we look at it, okay, these, whoops, excuse me, I'm going to grab my pen here. These cancel out, right? And I get frequency, right? Frequency is equal to the velocity of a wave divided by the wavelength. Okay, so that's another way to do that. So here's that. Okay, that's how we find frequency. And then we're going to do something really similar over here if we want to find wavelength. So if we want to find wavelength using this equation, okay, we look at this, we'll say, well, we're going to divide. So we divide by frequency. The frequencies cancel out, right? And we get this. We get wavelength is equal to velocity divided by frequency. And so there are our three equations that kind of that are based off of the same thing, right? And you might want to write those down and make sure that you know like which is which. Okay, so let's put those into practice real fast here. There we go. All right. So we're going to use the wave speed equation, right? What is the speed of a wave with a frequency of 8 hertz and a wavelength of 10 meters? Well, if I look at this, I'm looking for the speed of a wave, right? Well, speed, velocity is equal to wavelength times frequency, right? Cool. So we do this. We do wavelength times frequency, and we get 80 meters per second. 10 times 8, right? Okay, next one. What is the frequency of a wave? So here we're looking for frequency, right? And remember this, frequency is equal to velocity or speed divided by wavelength. Okay, so we'll set that up. I'll take my velocity or my speed right here. I'll divide it by the wavelength. Okay, and I get 20 hertz. Okay, remember hertz is per seconds, right? Okay, that's slash seconds. So the units kind of work out, you guys. All right, last one here. What's the wavelength of a wave? So here we're looking for wavelength, right? Traveling with a frequency of 16 hertz. If we remember this from the last slide, you guys, right? Okay, we take our wave speed, we divide it by our frequency, and we get our wavelength, which is 5 meters. If you notice here, you guys, here's our units, right? Speed is always in meters per second. Frequency is always in hertz. Wavelength is in meters. Awesome. All right, you'll be asked to do some of that on the assignment that goes with this. Okay, let's talk a little bit about the actual speed of waves. Okay, how fast do waves actually move? So if we think of waves, one of the first thing that comes to mind for me is the ocean waves or water waves. Okay, ocean waves, I looked this up, their speed varies anywhere from 10 kilometers per hour to over 50 kilometers per hour. Okay, and I'm just talking about regular ocean waves. Okay, I'm not talking about tsunamis or anything crazy like that. Those can travel a lot faster, actually. Okay, but I'm talking about regular ocean waves, 10 to 50 kilometers per hour, right? And I put those in kilometers per second, and you'll see why in a second. That was funny. You'll see why here in just a little bit. Kilometers per second, not very impressive, right? Okay, now what determines the speed of like an ocean or a water wave is the wind and the depth of the water and other factors that come into that. So how long the wind has been blowing, all kinds of stuff like that. Okay, next thing is sound, you guys. Sound travels a lot faster. It travels at 3.343 kilometers per second. To put that in maybe a little bit easier way to understand, it's 343 meters per second. So you can think about this. It would take a sound wave about 1 second to travel 3 football fields. Okay, so to think about that, you know, if I was standing up at my room at the high school in the science wing, and you were all the way down at maybe Whitworth, like way down at Whitworth, I'm on the playground, and I made a loud sound like I lit off a firecracker or something, it would take about a second for that sound to get to you there. Okay. All right, next one is light. Light waves travel at a speed of 300,000 kilometers per second. So that's why I put all of these different speeds in kilometers per second, is because to compare it to light, okay, there's no comparison, right? Light is way faster. Okay, it travels at a very high speed. The reason I bring this up is because I want to talk about waves and energy, and particularly light. Now, when we talk about energy, you guys, okay, we talk about amplitude. And remember, amplitude is the height of a wave from the midpoint. So we look at this. Here's the amplitude of this wave right here. Is this height right here from here to here? Okay, that's a lower energy wave. If we look at this wave here, it has a much larger amplitude, doesn't it? Sorry, I can't draw straight there, but you get what I mean. This one has a much higher height, and that tells us that it has a lot more energy. Okay, now that's in general. But things get kind of weird about light. And this is where things are going to get a little funky, you guys, but hang in there with me. I'll try and make this as understandable as possible. Light waves can act like particles or waves. That's weird. Okay, what's going on, Flugum? Well, here's the deal. Scientists have been looking into this for well over 100 years. In fact, Sir Isaac Newton first hypothesized about light back in the 1700s. Okay, and they've been throwing around ideas since, and we have a better grasp on it now, but it's still a bit of a mystery, I think. So the first thing about light we need to know is this is something called the photoelectric effect. And I want you to think of like solar panels when you think of this. Okay, so with light, and we have a piece of metal and we shine light on it, it gives off electrons sometimes. Well, when certain frequencies of light hit it anyway. If you notice here, it says frequencies of light. Okay, amplitude doesn't matter. It doesn't matter how bright the light is, you guys. What matters is the frequency. Okay, so if you look here at these waves that are hitting this piece of metal in the illustration, they all have a similar amplitude, okay? But the difference is their frequency, right? This one's a lot shorter, this one's a lot shorter. The red one here is longer. So amplitude doesn't matter how bright the light is, what matters is the frequency. How can that be if light's a wave? Shouldn't amplitude matter? Okay, because it takes energy to make an electron go off. So what's going on here? Well, it took a genius to kind of explain it. This is Albert Einstein here, at least a picture of him when he was young. He didn't have the crazy hair yet, right? Albert Einstein in about 1900 theorized this. Then, well, if light does that, then it can be like a particle. And he called those particles photons. Okay, so we call particles of light photons. The energy of a photon depends on the frequency, not the amplitude. Okay, and we know this because particles actually, their energy depends on frequency and not amplitude. So this helps explain a little bit about the behavior of light, but it makes things more confusing because light isn't just a particle. Okay, and our evidence shows us that. Okay, so why do we think light is a wave? Well, it comes down to this, right? Something called the double slit experiment. And if you choose, you can try and replicate this at your house. It's pretty easy to do. Okay, instructions are in one of the assignments. So you take a light source and you show it through two parallel slits or openings. Okay, and you would think if I showed a light through two narrow openings, you might see two lines. But instead, you see this right here. You see some kind of pattern that looks like this. And you may not see all the colors, okay, but you'll see something like this, okay, so where you have a dark spot and then a line and then a dark spot and a line and so on. Now, this is really similar to how water waves behave, because if I do a double slit experiment with a water wave, you can see the water waves coming in from the bottom here, going through these two slits, and then they kind of radiate out. If you notice, I get a place where there's no wave and a place where there's a wave and no wave and a wave, okay? So this kind of shows us that light is like a wave. And if you want to, if you have time, you can watch what's a Veritasium video. It's a channel on YouTube where he actually does this experiment and he takes it out in public. It's kind of cool. So check it out. So what's going on with the double slit experiment, you guys? Okay. Well, waves, as they go through the slits, they overlap and they interfere with each other, right? Just like in that picture with the water waves. And there's two kinds of interference, you guys. You have constructive interference, where when the waves come together and their wavelengths match up, they make a bigger wave, right? And then there's destructive interference, where when they come out and they match up, right, they interfere or basically cancel each other out and you get nothing. And that's what's happening here in these blank spots, is the waves are lining up and you are getting them canceling each other out from each slit, and that gives you a blank spot. In the brighter spots, that's where the waves match up. You see the different colors because you have different wavelengths for different colors. Okay, so that's why we kind of think that light is like a wave. So to kind of summarize this, you guys, light exhibits behavior that's like a wave, right? The double slit experiment. Light also behaves like a particle, okay, as shown by the photoelectric effect. So it kind of is a mystery of both things. Now, I don't know that this clears things up, but I want you to kind of try and explore this idea a little bit more, as well as the wave speed equation that I have. So there's two assignments that you can choose to do. Okay, you only need to choose one of them. So one of them is just like a regular worksheet with some problems and stuff on it. The other one is kind of a little bit of a mini project for you to do at home, where you're going to kind of use some easy to get your hands on things and try building and measuring some things. Okay. Well, cool, you guys. I hope everything is going well for you and you're staying safe. And I really, really hope to see a lot of you guys next year back at school at some point. Okay. Well, thanks a lot and take care, you guys. And I will see you later. Bye-bye.